So last week we introduced addressing mechanism in internet, and we discussed about classful addressing. Classful addressing is especially important because even if it is not used anymore, all the allocation of special addresses to special purposes comes from that mechanism, and this is the table of the addresses that are always reserved for special purposes. So let us review it briefly. The first is the network address. For each IP net, you have a network address that is the network prefix. This address is part of the block of the addresses, but it cannot be assigned to any host or any interface. So you can never use it as a source or destination IP address. And it's composed by the network prefix and zeros in the host ID. Then there is the direct broadcast address, specific value for net ID and all ones for the host ID can be used as a destination IP address. And the meaning is that once a packet arrives into the destination network, then it should be broadcast to all the interfaces of the network. Limited address broadcast, all ones in net ID and also in host ID, used as a destination. It means this packet has to be broadcast in this specific network. But then, since it is called limited, because packets that have this broadcast address can never be forwarded by any router of the network to any other network. So, like the limited broadcast address is like a bomb that explodes locally. The direct broadcast address is like a missile that you send and then explodes at the destination network. However, most of the networks don't accept direct broadcast packets. So when they arrive to the destination, they are usually discarded. Then this host on this network, all zeros, can be used as a source IP address when an interface does not know its IP address, so its interface when it is asking for an address. Specific host on this network for direct forwarding to a host as a destination. We can put 0 at 0 or the net ID because the network is the local network. And loopback is used to test the network interfaces or packets that are sent with the data address starting with 127 at the first byte arrive to the network interface of the host, but then I sent back to the operating system. And then you have the blocks of the private addresses that can be reused anywhere in internet, but they can never leave a so-called private kingdom. So a part of the network that is managed, that is supporting private addresses. When packets are getting out of this enclave, this part of the private managed with private addressing, they must undergo a packet, an address translation using, for example, a NAT or so. The network address and direct broadcast address have a specific impact on the assignment of addresses on a block corresponding to a net ID, because usually if you need a network that corresponds to a block of addresses so large that you can assign addresses to all the interfaces that are working or active in the network. So if you start by counting the number of interfaces, that includes both host interfaces and interfaces of routers that are connected to that network, then you have a requirement in terms of the number of hosts that must be addressable, or the number of addresses you need in that network. And you have always to add 2 to this number, because in the block you have to assign addresses to all the interfaces, but then you have also to count that there will be one address dedicated to the direct broadcast and one that is the network address. Okay, so if, for example, you know that you have 100 hosts, you cannot satisfy this host with 100 addresses. You need at least 102 addresses in the network. Obviously, the network size is always an integer power of 2, however, as you can understand. So this is about special addresses, and let's go back to the classful system. If we plot here on this pie the address space of IPv4, which is all the numbers you can obtain with 32 bits. That means 2 to the 32 numbers. Then we can partition it according to the different classes. And if you do this, you notice that class A takes 50% of this pie. Class B, 25%, so 1/4. Class C, 1/8, and then class E and D takes together the other 8. And so it means that most of our addresses are in class A. So the number of addresses you have in class A is by far larger than the number of addresses you have in class B and class C. This situation is not very satisfactory, because at the beginning of the internet, local networks were relatively small. So there were a lot of network prefixes available in class C. Each of these prefixes corresponded to a block of 256 addresses, and these 256 addresses were enough for the usual number of interfaces connected to a physical network at that time. But today, this is not true anymore. If you even think about a small campus or a small company, the number of addresses is much larger than the number you can have with the class C network. Instead, in class B network, you have 2 to the 16 addresses available in each network, which is a very large number. So it's oversized compared to the needs of most cases. But worse that the number of class B networks is much smaller, and so if you start assigning class B blocks because classes C are not enough, then you run out of network addresses very soon. And so this situation was not satisfactory. This classful system was really too rigid, and so it was overcome by basically 2 techniques. So there are 2 ways to modify this thing. One is called subnetting, and by subnetting, you can take a network, a block of addresses that is corresponds to a network prefix, and partition it internally in a way that is completely free. So you are not obliged to follow the classes when you are doing subnetting. It would not make sense. Subnetting was effectively applied, especially to subdivide the networks inside organizations. But then still the system was very flexible, ossified, because there was still the classful mechanism for to manage the overall networks assigned to different companies. And so the classless interdomain routing was introduced later, which is a generalization of subnetting. Now we will have a look to subnetting, and then also to CIDR, CIDR, to understand how this classful system can be overcome. So, subnetting is related also to the management of addresses when you have to open or to operate an IP network. Since, as we said, IP addresses have to be unique, they can not be assigned in a free way. There is an entity that is in charge of assigning addresses in a correct way, so to be sure that you never have duplications. And this is called ICANN, and this is subdivided into different regional entities. Each time the administrator of a network wants to receive a block of addresses that corresponds to an ID, the administrator has to query the regional internet registry, which is the part of this system that is responsible of a specific zone, of a specific regional area. And so a formal request has to be submitted to the RIR, and the RIR will assign a block of addresses after having checked all the things related to the identity of the administrator and so on. This is a long process and complicated. So when you have a block of addresses, if you want to partition it for your internal purposes, it would be really ineffective to have different blocks assigned from the RIR. So, for example, if you have a block that is /16, so a class B network, and you have different departments in your organization, you want to split this network into various subnets in terms of partitions of this overall network into sub-blocks of addresses. If you have always to ask or to declare this internal division to the RIR, it's really inefficient. Moreover, also, once you have assigned different blocks, it's difficult to change the internal architecture. So, in order to solve this problem, the subnet system was invented, and by subnetting, we mean that the local administrator of a network is entitled to create internal subdivisions or partitions of the network and so also of the block of addresses without declaring anything outside of the regional internet registry. Uh, um, Not only we don't have to declare anything to the regional internet registry, but he will not declare anything also to the rest of the internet. So this subdivision is only internal. When a packet has to reach a destination that is in this network, that is, for example, 131.175.0.0 is a /16 network. In the rest of the internet, it will be sufficient to know that the destination network is this one, the big one. It doesn't matter what is the particular subnet that destination belongs to. All the packets that are going to this network are routed in the same way. Once they arrive inside the network, so once they are processed by routers that stay inside and belongs to the network, then the specific subnet starts to matter in terms of routing. How can we achieve this this effect? Very simple. The trick is to extend the network prefix. So the overall network, the one that is recognized by outside in the rest of the internet, has a network prefix of a given length. For example, in this case, 16 bits. So it's a class B network. In the routing tables of routers outside this network, the network is always identified by its network prefix and a net mask that indicates /16 or 16 bits as length. Okay. When the routers are inside the network or are in the subnetted area, they will use an extended network prefix. By extending the original prefix, so that is 16 bits, by a number of bits or further bits that are regarded as part of the network prefix. And in this part, that is the extended part, you have the subnet ID, so the identification of a specific subnet inside the overall network. Obviously, this will mean that you have to give up some of the bits that are used for the host ID. But this is not a problem because in each subnet you will have less hosts, a number of hosts that is smaller than the number of hosts of the overall network. How many subnets you can define? Each time you add n bits to the original network prefix in order to have the extended network prefix, you can set up 2 to the n power n subnets. Okay. So each time you extend the network prefix of 1 bit, you can set up 2 subnets. 2 bits, 4 subnets, 3 bits, 8, and so on. So, what happens to the packets when they are routed in the different routers? If the router is outside and the packet is outside the network that is subnetted, only the original network prefix matters. So the IP address that is reported as a destination IP address will be checked in the routing tables using the default mask, using the original net mask. Okay, in this case, it's a class B network, so the default mask is the mask default is 255.255.0.0. So when you apply the AND operation, the result is the original network prefix. Inside the network that is subnetted, routers will apply the subnet mask, which is longer. So the result will be the subnet prefix or the extended prefix. And you can see, for example, here that this subnet mask is .192. .192 means that it's 1, 1, and the rest is zeros. So here, the extension of the original net mask is by 2 bits. So you have 4 subnets. Okay. So when a packet comes into one of these routers that are internal routers, the router applies the subnet mask, and for instance, in this case, this packet has 72 in the second byte as a destination address. This means that you have a 0, 1. 72 means 0, 1, 0, 0, 1, and then 3 zeros. So the first 2 bits are taken in order to understand what is the specific subnet of the destination, and here you have the resulting network address that is 141.14.64, meaning that the destination belongs to the subnet 01. Okay. So simply by changing the subnet mask, you can obtain this effect of filtering packets in a coarse granularity outside the network, on a finer granularity inside the network that is subnet. This is very useful, and if we are adding a subnet mask of a given size, we can create a certain number of subnets. But there is a further improvement we can do, because when you fix the subnet mask, then you have the number of subnets that you have created, and you have also the size of each subnet. But if the subnet mask is of a fixed length, all the subnets that you are creating has the same size. Okay? So here, for example, you can create 4 subnets, each one with a host ID of 8 plus 1, 2, 3, 4, 5, 6, 8 plus 3, 14 bits. Okay? They are all of the same size. Sometimes this is a problem, because internally in your architecture of your internal network of your organization, you may have physical networks that are smaller, larger, have more or less number of hosts to be assigned. So the further improvement is the variable length subnet mask, VLSM. In this case, by using the variable length subnet mask, you can create subnets, internal subnets, in a more flexible way, creating subnets that are large or small according to the actual need. For example, if you have a company where you have a computer room with 200 hosts and a secretary office with only 4 hosts, and you want to create a subnet mask without variable length subnet, without the variable length system. Let's say that you are using the subnetting with an extension to 24 bits. You can create subnets of size 256, all of size 256, which is good for the computer room, but very much oversized for the secretary office. So if you stay with this solution, you will lose a lot of addresses, and the addresses are a precious resource, because you always have to try to assign all the addresses of your block. So we can apply this variable length subnet mask in order to support to differentiate the size of the internal subnets. This, of course, has an impact on the routing protocols. Now we are in a system that is not the classless, the classful system. And before, in the classful system, the first bits of the an IP address were used to identify the size of the network. Now we have we don't have any way to identify the size of the network from the value of the addresses, because we can create a variable length subnet masks. So this means that the routing protocols must carry not only information about the prefixes, but also together with the prefix, always a specific subnet mask or net mask that is associated to that prefix. Not all the protocols were able to support this feature. So, for example, RIP1 was not suitable for this purpose. So now other protocols are used that support. Let's consider an example that is quite understandable. So you have this network, which is composed of different physical networks, 4 that are connecting variable number of hosts. One is with 100 hosts, 2 with 20, and 1 with 10. And then we have 3 routers inside, these are internal routers. They are connected each other by point-to-point links. If you remember, when you are configuring a router, you have always to assign to each interface a specific IP address, and 2 different interfaces cannot be connected on the same IP net. So this means that when you are connecting the routers with point-to-point links, each of the link is an IP net itself. It's a very specific IP net where you have only 2, you need only 2 assignable addresses, because you have only 2 interfaces. But you know that since this is an IP net, you actually have to take into account of the network address and the broadcast that are always reserved. So actually you need a block of 4 addresses for the point-to-point. So now we need blocks of sub-blocks of different addresses. If you try to configure this network without using the variable length subnet mask technique, then you result in a lot of waste, or it's even impossible to subnet this network. Because, for example, here you have 150 total hosts if you count all the networks. So with 150 total hosts, in principle, the class C network would be enough, also including local projections. But if you try to subnet, you have also to create 7 subnets, so 4 for the LANs and 3 for the point-to-point links. So with 7 subnets, you need at least 3 bits for the subnet ID, okay? Because otherwise you cannot define 7 different subnets. If you don't apply variable length subnet mask, then you have to use the 3 bits. And so the 3 bits, with the 3 bits, you are left only with 5 bits for host ID, which is okay for, so it means 30 hosts or 30 assignable addresses per subnet, which is okay for all the networks except the one with 100 hosts. So this is not the solution. The solution is this one that you see. And this graph also shows you what is the procedure when you want to subnet a network with different needs in terms of size. So first of all, we start with the original network prefix. In this case, is the 192.168.1.0/24. So we are in the class C network. Okay, so we have 254 addresses to address that can be assigned to the host. 156 addresses in all, but as usual you have the two reserved addresses. So once you start with the overall network, the first thing is to consider the network with the higher number of hosts. And the first subnetting step has to be designed in order to satisfy the larger subnet. In this case, the larger subnet is the one with 100 hosts. With 100 hosts, you always have to ask what is the closest and higher number that is an integer power of 2 that includes that number of hosts. So with 100 hosts, the closest is 128. 64 is not enough. 256 is the overall network, so it's too large. So it's 128. So you have to create a first subnetting, creating at least one network with 128 addresses. So it's enough to increase the number of bits of the subnet ID of the network prefix by 1 bit. In this case, you split the overall address space in two parts. There are two blocks of 128 addresses. Then the first block is assigned to the PCNet, the network with 100 hosts. And it's enough because you have 126 addresses that are assignable. And so this is already done. Then you have this block of 128 addresses. You start splitting the block in a recursive way. So you consider the next networks with the higher number of hosts, the highest number of hosts. In this case, there are two networks with 20 hosts to be addressed. 20 hosts, the closest integer power of 2 is 32. 16 is not enough, 32. So with 32 addresses, it's okay because you have 30 addresses that are assignable, larger than 20. And in this way, you can assign two blocks to the two networks that the two LANs with 20 hosts. Here we started with a block of 128 addresses. We need blocks of 32 addresses. How many blocks we can create? We can create four blocks of 32. So 4 blocks of 32 stay in one block of 128. We started with /25 as prefix length. We want to create 4 subnets, so it means that we have to extend the prefix by 2 bits. Okay, so from /25 we are at /27, and we have created the 2 blocks. The first 2 blocks can be assigned to the LANs. And then we have other 2 blocks remaining. Each of them is size 32. We have another LAN with 10 hosts. 10 hosts means that the closest integer power is 16. So we can assign a block of size of 16 addresses to the network. And here we have a block of 32 that is free. We can split it into two blocks of 16. So we start from slash 27. We extend by 1 bit. We create two blocks. Okay. Now we are at slash 28. The first block is assigned to the LAN. We are left with one block of 16. This block of 16 is enough to create the four blocks for the three blocks for the point-to-point connections. Okay. Each of them requires only 4 addresses. So you have you start with a block of 16. You can create 4 blocks of 4 addresses each. It means that the extension is of further 2 bits from slash 28 slash 30. And so at this point, the assignment is complete. We have assigned blocks to all the subnets, and all the hosts can be addressed. And we have still some some blocks that are left unused that are available for further extensions. Okay. So this is the mechanism of subnetting that is applied usually. And you can see that in the end we made it with a class C overall block for the overall network. And here you find the complete assignment. You can see that we have the blocks assigned to the 4 LANs and to the point-to-point links. For each block, here you have reported the network prefix, actually the subnet prefix. So, for example, for PCNet, the subnet is 192.168.1.0/25. Notice that that address of PCNet is exactly the same as the rest of the overall network, but the net mask is different. Here is a slash 16 and slash 24. There is a slash 25. Okay. So they indicate different networks. This is the overall network that is on the XR. Even if the address per se is, if you look at it without the net mask, is the same. And this is why in this scenario, net mask must be always associated with network addresses. Questions? Yes.
The link handler only repeat.
Yes.
And I consider also the link as a network.
Yes. So this is why you need also a net address and a broadcast address. They must be there because otherwise this is not And this is the pie chart. It is always very useful when you do some netting, because you can visualize the size of the different network that has been created. So the whole pie represents the overall network, the class C network. And each time you add 1 bit to the net mask, you are splitting the pie into parts, or you're splitting a sector into parts. So in the first subnetting, we started with slash 24, and we added 1 bit to create the first network for /25. This means that the space was split in two parts. One was assigned to the LAN, is called PCNet. The other one was available. So the other one was split again by applying the subnetting in a recursive way. And first, if you remember, we had to create 4 networks. So this means that the network prefix was extended by 2 bits. And so the half of the original pi was split into 4 parts. 2 of them were assigned to 2 networks, the other 2 LANs. The other one was split again. It was split first by increasing of 1 bit, so it was split in 2 parts. One remains empty, available. The other one was subnetted again. It was subnetted once to create the final LAN, and then extending by the other 2 bits to create the point-to-point networks. And here you see the whole map. So in the routing tables, you have always to specify the mask, the network prefix and the mask, that is, or equivalently, the network prefix associated with the length of the prefix, because the mask is really has an impact on how packets are routed. And also the protocols, as I already mentioned, must always carry information about the network prefix plus mask or length. Remember that the net masks are never carried on board of the IP packets, the data IP packets. They are always carried by the routing protocols used to write the content of the routing tables, but never inside the IP packets. The IP packets always have a pair of IP addresses that are complete. They are always 32-bit long. It's the way they are read and processed that changes according to the net mask. But the packet itself has a unique IP address. And this is also another reason why the longest prefix matching algorithm is very important. Imagine that you have a packet that is destined for a certain destination, for example 11.1.2.5, and routing table with several entries. Especially if you're using variable length subnetting, can happen, as we have seen in the previous example, that you have addresses that have the common part, the common first part, and then they are different in the other parts. So, for example, here you have an entry that is 11.0.0.0/8. Then you have 11.1/16, 11.1.2/24. These 3 entries are related to the second entry is a subnet of the first. The third entry is a subnet of the second, and also a subnet of the first. Okay. So once the packet arrives to this router, which has the routing table supporting subnetting in that specific area, what is the final decision to take? If you are adopting the longest prefix matching algorithm, the final decision will be to send the packet towards the network that matches with the destination address, but that matches for the longest number of bits. So it means to send the packet to the matching network that is the smallest possible. Okay. Or better, equivalently, it means to send a packet where the router has the most precise routing information. Because here in the routing table, the router knows that there is a large network and a smaller subnet and then a subnet inside that subnet. So the most precise routing information is surely this one, the last line, because it's a -24, 24, so it's a small target inside a larger targets. So according to longest prefix matching, the packet will be sent to this destination, okay, to this output actually. Okay. So this subnetting technique is used inside, let's say, to configure the internal part of networks. And then the second step that led outside the classful mechanism was the classless interdomain routing, CIDR. The basic idea is to completely eliminate traditional distinction between class A, class B, and class C. When a network is a block of addresses is assigned to a network manager, it can have any size, and the size is specified by the length of the part of this block that is identifying the network prefix. So actually a block of addresses that corresponds to a network in the classes in the domain routing is assigned by providing two numbers. One is the prefix and the other one is the net mask, or the length of the prefix. So routers do not make any assumption on the base of the leading bits, so they require an explicit prefix to determine the division point. And of course, this implies that the routing protocols must support this capability. It was the same also in the subnetting mechanism, but usually when you are subnetting, you are inside an autonomous system, so the routing protocols involved are the ones that act inside the autonomous system. For example, OSPF and the RIP. Between autonomous systems, there is another protocol that is different, that is BGP. Also, BGP must support the transmission of prefix text. And in fact, BGP version 4, which is the BGP currently in use, supports this, this feature. So in the classless system, the concept is can be also visualized by considering this kind of representation. The full address space of, for example, IPv4 can be a line represented as a line, a number line, with all the numbers from 0 to the 32 minus 1. Obviously, this line has only integer values, so it's actually a discontinued domain. A block of addresses corresponding to a network that is assigned to the given network is a segment on this line. So, for example, here the block 128.9/16 is a segment of length 2 to the 16 located in some place on the line. And now that the network size can be variable, segments can be of different length. So with this block 128.16, 128.9/16 can be adjacent to another block that is, for example, 128.9.255.255. Sorry, this is the boundary of the block. So another block that is size, for example, this could be /24. Okay, so smaller segment. The block corresponds to an interval of numbers with these two blue numbers. One is the lower boundary, the other one is the upper boundary. So in this case, we have 128.9.0.0, and on the other side, 128.9.255.255. How can you perform what is called IP address lookup? That is the operation a router performs to understand if a certain destination belongs to a certain node. This representation is just the operation of locating a point on the line number on a specific segment. Okay. So, for example, here this address 128.9.16.14 falls into this segment. So it means that this destination IP address belongs to the specific network. So when we are doing the lookup operation in a router, we are basically locating a point on of the line number inside a specific interval. This representation is quite effective because then you will see that it is used and very useful with some of the algorithms that we will explain. How to define these segments? We just need for each segment two values. One is the prefix and the other one is the length of the prefix. The length of the prefix translates into the length of the segment, and the value of the prefix translates into the position of the segment in the line number. Now, what happens when you are doing subnetting, or when you are generalizing subnetting to the whole network, as we do in the CIDR mechanism? When you have a routing table of different entries similar to the one that I have shown you before, this one, okay? This is equivalent to have the line number overlapping segments. Here, for example, you have the segment 128.9/16 and the segment 128.9.16/20 is overlapping, partially overlapping with the first segment. And then you may have other overlapping segments, like for example these two, which corresponds to /24 networks. Okay. So when you are doing IP address lookup, you have to understand what are the segments that contains the point representing the destination IP address. And in this case, you may have more than one segment containing the point. For instance, in this case, you have this segment here, the /16, and then also this segment, the /20. Not the other two small segments, because this specific address is intermediate, is outside both the other addresses. In fact, here you have /9.16.14. This is 9.19, this is 9.25, so it's not matching with any of the two /24 entities, but it's matching with the /20 and with the /16. Okay. The longest prefix matching algorithm obliges you to consider as a final result the the segment that is the smallest one that contains the point. So in this case, the final result will be 128.9.16/20 because the point is containing the two segments that are overlapping, but this is larger than this, so longest prefix matching is with the second one. Okay. And so this is basically the operation that is carried out when we are doing IP address lookup in a router, and we will study in the next part of the course what are the effective techniques to carry out this operation in a fast way that implies a small complexity. So somebody asked last time if the so-called linear search is a good alternative, is a good way. The linear search means that is what you would do manually. So when you have a routing table and an IP address, you start looking for matching the first line, the second, the third, and so on, until you arrive at the end of the table. And so the number of comparisons that you do is proportional to the number of items you have in the table. Maybe if you sort the table by putting, for example, the longest prefixes on the top and the shortest one in the bottom, statistically you may improve the number of times you do the check-ins because you stop early as soon as you find the first positive match. But still, the order of magnitude of this, the complexity of this operation is proportional to the number of items. And the number of items in a routing table is really large, can be even in the order of 10,000 or so. So by the techniques that we will describe later, the complexity is not linear anymore with the number of items, but can become different. For example, linear proportional to the length of the longest prefix that you are considering, which is much better. With the CIDR system, the concept that we have adopted in subnetting can be extended also to the whole internet. This is a practical example that you can consider to understand better this concept. Let's assume that you have an internet service provider. This internet service provider is large and it has both business customers and residential customers. And then among the business customers, it has, for example, these four companies, company A, B, and C and D. So each of these companies must have a network to be allocated. So, for example, company B has two networks, /24, company C has other two networks, /24, company B and A have a larger portion of subnet, a larger number of subnets. The partition of the network of each single company is important when packets travels inside the network of the company, but it's not relevant outside. So each company can be represented inside the routers that are inside the internet service provider with a single item, single network prefix that is aggregating all the network prefixes dedicated to the companies. For example, here you can use a /23 that is aggregated at 2/24, and /22 in this case aggregating 4/24 networks, and /21 in the other case. This is it's called root aggregation, and it's basically the same concept that we have seen in subnetting, but applied on the other sense. So in subnetting you are subdividing, here you are aggregating. But the concept is always that you have a large network corresponding to a single net address, which is representing a plurality of smaller networks. Then each of these aggregated addresses dedicated to the companies belong to a block that is the block of all the business customers of the ISP. Okay. So here we can adopt another step of aggregation, aggregating all the addresses of each business customer into a single address, which is a /20. And then this address is relevant inside the network of the internet service provider, but outside the network of the internet service provider is not relevant, because the important thing is to reach the internet service provider. And so all the addresses of the internet service providers can be aggregated into a single address when you are outside the network of the general internet. What is the benefit of this mechanism? Is the reduction of the number of items that you have in the routing tables of the routers. Okay? Because in a router that is in internet outside that ISP, you have a single entry. Okay? And that entry represents all the network of the ISP. When you are getting into the ISP, you have routers that are here. You have two entries, one for business and the other one for the other customers. But you don't need to distinguish between the different companies. When you are getting into here, then you start distinguishing the different companies and so on. If you export all the detailed information at this level outside the internet, then you will have huge routing tables that are really unmanageable. So basically, this is a root aggregation, and it's very important. It's the mechanism that it is used today very extensively, and we can use it once we are outside the classful mechanism that we have seen before. So routing aggregation is usually exploited very widely, but sometimes you need also to say break this general trend and export in routers that are outside a network addresses that are also specific. Not only the general address, but also addresses that are specific. This is called the exception prefix, or exception prefix routing. And in the address space, it means that you have a large segment that is reported in a routing table outside, and also a small segment that is overlapping with the large segment. When we need this kind of exception routing, there are very specific situations. This is one example. So today, the IP addresses are assigned on a geographical base. So, for example, if you are a company in Europe and you ask for a network, then you will be assigned a block of addresses that belongs to the larger block that is used for Europe. Okay. Let's say in Paris, a company asks for a block that is /7. Okay. And so this block is taken from the wider block of the European region. Actually, that /194/7 is the block for the European region. So the address that will be given to that specific company is taken in this block. Then assume that this company wants to open a subsidiary in another place in the world, for example, in South America, in Mexico. So in principle, this company should ask for another block of addresses that it would be taken from the block dedicated to South America, and things would work. But this means that all the equipment of the company that is located in the Mexico City site, has to be reconfigured with changing all the addresses that were originally configured when the equipment was in Europe. And so it's not really comfortable for the company. So usually companies, even if they open sites in other places, they keep the original block of addresses. So the IP address of the site of the company that is here, the headquarters that is in Mexico City, the IP addresses are the same, are taken from the original block that was assigned to the company when it was in Europe. So now, what happens if a packet that is addressed to a specific host of this company arrives into a router that is, for example, located in New York? If this router is only a table that is aggregating addresses at the maximum possible level, it will have two different entries, one for Europe and one for South America. So when the packet arrives to the router that is in New York, since the address belongs to the block of addresses of the European region, it will be sent to Europe. Okay? So once it arrives here, then there must be some way to send the packet to the correct destination that is in Mexico City. So the packet has to come back to America, going from Europe once and come back to America. So in order to avoid this, we can create an exception routing entry in the New York router. So in this router, there will be another entry that is a subnet of the network of the European region, but with the indication of an output interface where to send the packet that is different. So all the packets to Europe are sent to this router, except the ones that are explicitly indicated into another line that are sent to South America, another line on the table. So when a packet is addressed to a host that is in Mexico City, headquarters of the company, it will arrive to the network to the New York router, and thanks to the longest prefix matching rule, it will be sent to Mexico, not to Europe. A similar situation is this one, when you have an organization that is subscribed to a given service, internet service provider, and so it obtains a network block of addresses that belongs to the overall block of addresses of that internet service provider. Then imagine that this organization wants to change the internet service provider, so it makes a subscription with another internet service provider. In principle, it should obtain another block of addresses that belongs to the general block of the second ISP. But this implies that the organization has to reconfigure all the hosts and the interfaces with the new addresses. So this is not very comfortable. So the organization maintains the block that was originally provided by the first provider, and in the routers of this internet service provider, the new one, you will have an exception routing. Sorry, in the routers of internet, you will create an exception routing so that when a packet is sent that specific final network ID, so 200.25.16.0/21, it is sent to this second internet service provider. In principle, this block belongs to the larger block 225.0.0.16/16, that is the network of the former service provider. But when there is this exception routing configured on the routers of the internet, thanks to the normal square expression, it will be sent to the other route, okay, so the correct way. Okay. So this is basically all about this part. You have some extra slides where you find more examples and more information. You can have a look. So I think that we can stop here because it's already late. Next time we will start looking at the architectures of routers. So we are going more deeply into the topics of this specific course. Okay, thanks.